Okay, welcome back. We'll see what we have in store for us for day 11 of Advent of Code. Day 11, Dumbo Octopus. You enter a cavern full of rare bioluminescent Dumbo octopuses, which is, by the way, a valid word just like octopi. They seem to not like the Christmas lights on your submarine, so you turn them off for now. There are 100 octopuses arranged neatly in a 10 by 10 grid. Slowly gains energy over time and flashes brightly for a moment when its energy is full. Although your lights are off, maybe you could navigate through the cave without disturbing the octopuses if you could predict when the flashing lights will happen. Each octopus has an energy level, which we see here in the example. And later, the puzzle input will look like this. Okay, that's not too bad. The energy level of an octopus is between 0 and 9. The top left, for example, has an energy level 5. Bottom right has an energy level 6. You can model the energy level of flashes of lights in steps. At first, each energy level increases by 1. Then, if it's at 9 after the increase, then it flashes. What we mean by flashes is that the energy level of all the adjacent octopuses increase by 1, including the diagonals. If this causes an octopus to have an energy level greater than 9, sorry, I should have said greater than 9 above, it also flashes. This process continues as long as new octopuses keep having their energy level increasing by 9. Octopus can only flash at most once per step. Finally, an octopus that flashed during this step has its energy level set to 0 as it used up all of its energy to flash. So, for example, if this was a startup, all the 9s would cause a flash and keep adding to the cells around it. And it looks like we might have to keep track of the number of flashes. So after 100 steps, you'll get a total of over 1,000 flashes. Given the starting energy level of the Dumbo octopus in your cavern, simulate 100 steps. How many flashes are there after 100? Okay, I think I'm going to just hard code this one. Not even bring in any additional files. We are on day 11. And my puzzle input looked like this. And whoops, I don't need the quotation marks. And I think I'm just going to hard code this one since I'm intentionally keeping the difficulty level down. So we're going to start off with vector numbers. And that's for the real puzzle input, but like what we've been doing with the other puzzles, I want to start with the example, make sure that I could replicate the example, that is, get the exact same answers. Before I do anything really complicated. And I wonder if in R, if there's a way to just get the digits. So the digits command is not included. So we're going to have to hard code that, and I think I'm going to bring in the tidyverse after all to do that. Okay. So this puzzle input, we have 10 numbers. That means our matrix will be this many rows. And if we just take one of the numbers, then we would see that the number of columns is also going to be 10. So now next I want to create a matrix. I'm going to fill it with zeros, and the number of rows, I'm going to add 2 to m, add 2 to n, because I want a buffer on all 4 sides. So then finally, for the rows, I want to grab the numbers and fill everything in. Let's see, what did I do here? And that's not quite what I wanted. So I got the numbers in the correct places except for the last row for some reason. There we go. I had an off by 1 error. Because my puzzle input, I'm starting the indexes at 1, then 2, then 3. But for the rows, I was going 2, then 3, then 4. So that's why I had to make an adjustment. So now what we're doing is basically going through this matrix, and there are a couple more steps, but basically we're going through this matrix. Every time there's a 9, that's the so-called octopus flash, and then we'll do a calculation thereof. So let me What I'm wondering is if I should have just one matrix, or should I have 2 different matrices? Would 2 different matrices help me keep track of everything that's going on? So now, simulate the octopus's flashes. For is step already a reserved word? It is. So how about time step? Not time step. Okay. For time step in 1 to 100. What I'm doing here basically is avoiding a while loop here. And then going to do that same thing later. So for k in 1 through, let's say 1,000,000, I'm going to avoid a while loop here as well. Actually, that's why I'm avoiding the while loop. We're going to go through the matrix and keep adding 1 to the numbers. Let's see, how do I want to do this? So now I want to traverse matrix, avoid buffer in first and last rows and columns. So for I in 2 through n plus 1, for j in 2 through n plus 1, first we're going to add 1, to the current octopus. probably accidentally introducing redundancy. Let me reread the instructions. So what I want to do at first is add 1 to each octopus and then look after the flashes. That's what I want to do. So let's take the adding 1 to each octopus actually happens here, and that's going to happen in these rows and in these columns. So we're going to add 1 energy to each octopus, and we're avoiding the buffer. Now, as we're transversing the matrix, if the matrix value is greater or equal to 9, then the octopus flashes. So then what happens is add 1 to neighboring octopuses. So that's I minus 1 through I plus 1 for the rows, and then j minus 1 through j plus 1 for the columns. And then we also want to reset the current octopus to 0. This I'm also concerned about. This process continues as long as new octopuses keep having their energy level increase beyond line. Note that an octopus can only flash at most once per step. I think that's going to be automatically true because you only have 8 neighbors. So now we also need to keep track of the number of flashes. Start at 0, and then we add 1 whenever an octopus flashes. Now, technically, I'll be adding numbers to the buffer as well, the first row, first column, last row, last column, but at no point am I actually checking those numbers otherwise. So I might already be done with part 1. we'll see if we got it. What I should have done, the code is running for a while. What I should have done is if the matrix. Okay, so what I was about to say is if the matrix ran out of nines, then I'd stop. But with this instruction that each octopus can only flash once, I might have actually searched too many times. So let me take out one of the for loops and see what we're getting. So now when I check, I'm actually getting too many numbers here. So let me also, what I should do is double check that I even got like the first two steps right. There's first two time steps. So I'm gonna bring this time step down to 1, rerun everything, make sure I'm not running the puzzle input. And there were not supposed to be any flashes on the first go around, so this is actually kind of worrisome, I think. So what happened here? I'm trying to, this is the first step. So at this point, I have this matrix, which is starting off 5, 4, 8. And that's what I get here. After one step, the first 3 entries should be one number higher in each part, and that should be 6, 5, 9. The issue is that I got 7, 7, 1. So my code's actually being too ambitious somehow. So after one step, I really should have this matrix. It might be the case that I simply have an off by 1 error. No, that's not it. Because I still want to get an answer of 1,656. So what happens is that I got this matrix at the beginning, the one with the 659 in it, and I thought I had the flashes go off. But this should now, even if this number did activate, that should be a 0. Hmm. One thing I want to double check, if I do run this for 100 time steps, what does my M matrix look like? This number should not have been able to reach, or it should not be any 11 because the numbers surrounding it would not have activated previously. Another thing I'm surprised by is I'm actually getting numbers that are too big than what the puzzle entails. I'm actually, at the moment, the way I coded this, I thought I would actually be underestimating the number of flashes. Oh, oh. It said greater than 9, not greater than equal to 9. Is that what I'm doing wrong? Hmm. estimating. Let me go time step by time step again. So after one time step, there were 0 flashes. That's actually correct. After one time step, there were 0 flashes, and we should end up here with this matrix that starts off 6, 5, 9, 4. Now if I go, let me see if I can move this over. So now if I go to 2 time steps, we should have this matrix down here. But for some reason, I'm getting a 1 here instead of a 0. So what happened was this flashed. It added 1 to all these numbers. Which caused this number to flash, which added 1 to all those numbers. Okay. I think what I did was I didn't correctly interpret this last rule. Any octopus that flashed during the step has energy level set to 0. So that has to come after the whole entire check. And I do need another. So I need to create another matrix after all. And that's going to start off with a value of false. Keep track of which octopuses flashed. I'm going to change that value to true, that location to true whenever that happened. And then after the traversal, M where the octopus flashed is 0. And once again, reset this second matrix here. Okay, getting closer. So after 2 steps, it said 17 of them flash. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I'm getting much more than 17 actually. So what I'm saying is that if the octopus has not already flashed, go through this. And I think I do want that. Avoid wild code after all. Because we might have to traverse the matrix over and over again, just in case the chain reaction goes back upwards or to the left. So after step 2, we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 19, 25, 31, 35 flashes. My concern right now is that my code is so inefficient that it's taking 4 seconds for 2 steps. So to get to 100 steps, I will need, well, 4 times 50, 200 seconds. So I will need about 3 minutes to solve this problem. So if for some reason someone's watching a YouTube video, I'm going to hit play, or I'm going to run this for 100 steps to see if I can still replicate the example. It's going to take my computer about 3.5 minutes to solve this, so you might want to skip ahead. Okay, I'm back, and we replicated the example. That wasn't even solving the main puzzle. Now, I'm being really naive about this cautious loop here. So, if I have m rows, n columns, that means at most I would have to traverse the matrix. Is that 100 times? Per time step. So I think I should put m times n here. That's probably a better worst uppercase or worst case scenario, upper bound I should say. So now let me run this on the real puzzle input. I'm going to run this only for a couple time steps again just to get a sense of the timing. We got 14 milliseconds. If I run this for 10 time steps, we got maybe about 14 milliseconds. And I don't know if that's right. Hey, I got it right. Okay. So I was just being way too cautious before. Let's now see what part 2 brings for us. It seems like the individual flashes aren't bright enough to navigate. However, you might have a better option. The flashes seem to be synchronizing. In the example above, all the octopus flash. The first time all octopuses flash simultaneously is at step 195. Oh, jeez. If you could calculate the exact moments when the octopus will all flash simultaneously, you should be able to navigate through the cavern. What is the first step during which all octopuses flash? Now, I don't think the code's going to be hard. It's just I have no idea how big the number will be. And in advent of code, sometimes an answer like this would be somewhere in like the 10 million or so range. There's probably a smart way to answer this mathematically, but I'm really not the person to do that. So once again, I'm just going to run this over the example input first just to see if I could get that to work. We're not keeping track of the number of flashes anymore. And what we're doing is this main step here. If every octopus flashed, stop here. So if sum of m flashed is m times n, we're going to break, and that happens at every octopus flashed at time t equals timestamp. So now the issue is that my time step. The issue is that my time steps can go on for an unknown amount of time. In the example, this happens at step 195, so let me push up to time steps 200, see if my code works. And it replicates the example. Now, for the real puzzle input, I have a hunch that the people at Advent of Code designed this, so it's going to take more than 195. I'm going to push this up to 1,000 time steps just to see if the answer is in this time frame. And we did it! Woo! Okay, folks, our streak continues. I wish I had a better sign off, but I'm doing this slightly late at night at my time zone, so I just kind of want to call it a day, get some rest, and depending on whether or not I'm socializing with people tomorrow, maybe I'll see you tomorrow. Bye.